Good morning, friends. I'm Boris Hasselblatt, Secretary of the American Mathematical Society. For joint international meetings, the AMS supports the travel of invited speakers from the US, and on behalf of the AMS, I'm happy to introduce this address by Richard Kenyon. I believe that he and I first met at IHES as fresh PhDs when I was on a one-year honeymoon, and again in Lyon during my first sabbatical. This is related to significant career stages of his having taken place in France, including a habilitation, as well as several permanent research positions there. More recently, he moved to Yale University after a number of years at Brown University. And prior to today, we most recently met at MIT again, during a birthday conference for Jim Propp, a collaborator of us both. That means that my Kenyon number is 2, and you can look up your Kenyon number after this talk on MathSciNet. His research is highly cited, and he's a prolific reviewer on mathematical reviews. We all should be. An example to us all, and a great lecturer to boot. It's a pleasure to give you Richard Kenyon.
Thanks, Boris, and thank you to the organizers for having me here, and thank you for coming. I'm very excited to be here. There was a little snafu about the title in the online program. You may have noticed that the first line of the abstract somehow got promoted to the title of the talk. This is the real title, Webs and Dimers, and it's based on work I've been doing over the past just a couple of years. So with the people here, Dan Douglas, who's at Virginia Tech, Nick Ovenhouse is at Yale, Howlin Shi is now in industry, and David Wilson, who many of you know already. Okay, so let's get started. What's a dimer cover? Dimer cover is just a perfect matching of a graph. So here I have just a square grid graph, and perfect matching just means pair up the vertices into neighboring pairs. I'm going to call that a dimer cover, and one of the reasons we study dimer covers is that there's a beautiful way to enumerate them. We're studying random dimer covers. Okay, great. Due to Castellane and Temperley-Fisher in the 60s, they showed that the number of dimer covers of a planar graph is the determinant of a matrix, which is related to the adjacency matrix of the graph. And if you do this for the n by n square grid here, that's the formula you get. It's kind of a very mysterious and beautiful formula for the number. It's just enumerating the number of perfect matchings or dimer covers of that graph. Intriguing and weird, I would say. But another thing you can do with dimers is to take two independent dimer covers of the same graph and just superimpose them. Here I took a blue one and a red one, and actually they're slightly different. For the blue dimer cover, I covered all the vertices, and the red dimer cover, I just covered all the vertices except for the 4 corners. So at the corner, you see that there's only one blue dimer. When you superimpose the two dimer covers, you get these loops and chains, and sometimes double edges. And the chains start at the corners because they start blue, and then there's a blue-red chain, and it has to end at another corner, right? And that begs the following very simple question. What's the probability that A and B are connected by a chain, and C and D, rather than A and D and B and C? Since the chains are don't intersect each other, A can be either connected to B or to D, and likewise, for the other one. So what's the probability that in the union the corner connection goes that way versus that way? And of course, if it's a square like illustrated, the probability is exactly 50%, just by symmetry. But if you have if it's a rectangle or some more complicated piece of Z2, this is a non-trivial probability. And the amazing thing is that there's an answer which in the scaling limit the limit when the lattice spacing goes to 0, it gives you a very beautiful formula. So imagine we have some domain in the plane, like this peanut shape here, simply connected domain, and we approximate it with a very fine grid, square grid. And we do exactly the process on the previous page. We take two dimer covers, one blue and one red, we superimpose them, one which doesn't have the corners, so we get these paths. And you can ask, what's the probability that that the connection goes this way versus the other way? And the answer is here's the answer. You look at, in the limit epsilon goes to 0, this probability converges to the following cross ratio. You take the Riemann map to the upper half plane, you look at the image of A, B, C, D, phi of A, phi of B, phi of C, phi of D, and you just compute the cross ratio. And that cross ratio is the probability that they connect this way. And if you want the probability that they connect the other way, it's just 1 minus that, or it's another expression. So that's the content of this theorem. The theorem is more general. It also works when you have multiple points on the boundary. Here, for example, if I have 6 points, black, white, black, white, black, white, I can do the same calculation, but now the paths there are multiple ways that the paths can connect to each other, right? There's, in fact, 5 ways, some Catalan number, when you have this pattern of blacks and whites. And the answer for this particular pattern is, again, some nice rational expression in the z's, which are the images of the phis under the Riemann map. This phi is supposed to be the Riemann map from the simply connected domain to the upper half plane. So clearly something interesting is going on. This is some conformal invariance property of the union of two dimer covers. And this is not so easy to prove, but the resulting formulas are so pretty that it's really worth thinking about. And this is already 20 years old. So recently we wanted to ask the question, what happens if you superimpose 3 dimer covers or do something more complicated? Here I took a green one, a blue one, and a red one with some boundary conditions. But unfortunately, when you superimpose them, it's just kind of a mess. It's kind of a cloud of things. You don't see any internal structure there. But I want to tell you that there is one of the goals of this talk is to point out that there is some internal structure, and you can make a similar kind of calculation. Okay. So let me, here's now an outline. After that brief introduction, here's a little outline of what I want to do today. There's basically one main theorem which I want to get across as the main idea for this talk, which is a generalization of the Castellane theorem. The Castellane theorem is the theorem about counting perfect matchings of a planar graph. And so I have to define some things, and there's a little bit of motivation, and at the end we'll do some applications. Okay, so here's the setting. Everything is going to be a planar graph. In fact, a planar bipartite graph G. Although, there are generalizations of what I'm saying if you remove either of those quantifiers or both. But let's just stick for this talk to a planar bipartite graph, for example, that one. And we're going to put, at each vertex, we're going to put a positive integer multiplicity, vertex multiplicity, like here. And we're going to assign to each vertex a vector space of that dimension. So it's just a graph of vector spaces, if you like, of finite dimensional vector spaces. And now the edges are going to be naturally oriented from the black vertex to the white vertex. And on each edge, I'm going to have a linear map between the corresponding vector spaces. So on an edge label 2 to an edge label 3, I'm going to have a 3 by 2, a linear map from a two-dimensional vector, R2 to R3, which I can present as a matrix here. That's called a quiver representation, but for short, let's just think of it as a connection on the graph. Right? So your graph is just a collection of vector spaces and maps between them. But as a special case, when the multiplicities are all the same, if all the dimensions of the vector spaces are the same, equal to n, and all the maps are invertible, this has another name. This is called a GLN local system or a GLN connection. That's the case, we often care about this particular case, but our result is more general, and sometimes, as you'll see, the more general case is interesting as well. All right, so now that's the background data, these matrices. Now there's some combinatorial objects which are generalizing dimers, and those are called multiwebs. What's a multiweb? An N multiweb. It's an assignment to each edge of a non-negative integer. So it's a function on the edges to non-negative integers. And at each vertex, the sum of the edges around that vertex has to sum up to the vertex multiplicity here. So the blue here is my multiweb. It's just an integer function on the edges, which sums to the corresponding value at the vertex. So those are called multiwebs. Let's have capital omega sub boldface n, right? The set of n multiwebs. N is this vector of vertex multiplicities. And that's a finite set. Well, in order for it to be non-empty, you need some some equality here. The sum of the white vertex multiplicities has to be equal to the sum of the black vertex multiplicities. That's essentially the handshake lemma. But there's also some inequalities you need in order for this to be non-empty. Those are multiwebs. I'm not sure, it's maybe not the first thing you would think about trying to count, but at least in the case when all the multiplicities are 1, this is the set of dimer covers of the graph. I hope that's clear. So it's a generalization of the notion of dimer cover. Here's a statement of the main theorem, which, of course, I haven't defined either side of the equality yet, but the theorem is that there's a certain matrix whose determinant, the certain matrix K, which depends on the connection, whose determinant is the sum over all the multiwebs of some quantity, which is called the trace of the multiweb. And in the case of the dimer model, this is the standard Castellane matrix, and all the traces are 1, so it is, generalizes the dimer situation. Here's a very small application, just so that you can see that I'm not making stuff up. Let's think about the 6-vertex model or the square ice model. They're the same. What's the square ice model? You have a little water molecule. You take a bunch of water molecules, you plunk them onto the square grid so that the oxygens sit at the vertices and the hydrogens sit along the edges. And you have to, for the square ice model, you have to make ice, so you have to pack them in tightly so that there are no gaps. Every edge is occupied by 1 hydrogen, and every vertex is occupied by 1 oxygen, like that. And of course, there are many questions about the square ice model or 6-vertex model. This is a special case of the multi-web model. Over here, if I have this graph, the square grid with the extra vertex on the center of every edge, then I can put if I put all the white multiplicities to be 2 and all the black multiplicities to be 1, then a configuration, a multi-web will look like a square ice configuration, right? Every oxygen has degree 2, and every hydrogen has degree 1. So it's the same model. So if we can do some enumeration of this with some determinant, then we get some determinant enumeration of the square ice model. And in fact, there's a certain, if you know anything about the 6-vertex model, this is maybe for experts who know the 6-vertex model, there's 6 possible arrangements of molecules. There's six possible ways to put a molecule on there, 4 choose 2. And so there's 6 weights associated to the positions of the molecules. And if those 6 weights satisfy some equation here, this is called the free fermionic subvariety of the 6-vertex model. And that's the case where you can actually solve the 6-vertex model by determinants, and that's the case we can do in our setting as well. Okay. I thought, I don't know how many people know the Castellane determinant formula already? Not very many. So here's a very short description. you have a planar bipartite graph, G, and that graph has a bipartite adjacency matrix where the rows are indexing the white vertices and the columns are indexing the black vertices. And I'm going to throw in some extra signs. So rather than having a matrix, the adjacency matrix, which has zeros or ones, I'll put zeros or plus or minus ones. And if you put in the signs in the right way, so that around each face, the product of the signs is minus 1 to the L over 2 plus 1, where L is the length of the face. If I throw in those signs into the adjacency matrix, then the determinant of that matrix counts the number of dimer covers of the graph. And this is already 60 years old theorem. It's pretty easy to prove. You can prove it in your undergrad graph theory class. I've certainly done that myself. It's not very long, and it's kind of fun, but a very interesting little combinatorial exercise. So that's the sort of starting point of our situation. What we want to do is soup this up soup up this matrix, the K matrix, to a matrix which contains all our data, our connection data. So that's what we have is a graph. Oh, here my graph is just a square. It's got 2 white vertices and 2 black vertices, but on every edge, recall on every edge I've got a linear map between the corresponding vector spaces, right? On the C, this quantity C here is a linear map from a 2-dimensional vector space to a 3-dimensional vector space. So it's this 2 by 3 matrix, 3 by 2 matrix. So what I do is I make this new matrix in sort of the most naive way possible. I just take the original Castelli matrix, pretending like all the edge weights are scalars, and it's got some signs in there. But then I replace each scalar here by the corresponding block of its matrix entries. Right? So for example, here you see the C block becomes a 3 by 2 block of real numbers. So from these 4 linear maps, I construct this matrix of scalars, a scalar matrix K tilde. And it's got some signs thrown in. And while you may worry about, let's see, what is there to worry about here? I think I got all the ingredients, but that's all there is. That's all there is to it. It's kind of, you do the most naive thing possible. Notice that it's a square matrix because the sum of the black multiplicities equals the sum of the white multiplicities. Right? Remember the rows are indexing the white vertices. This is and the columns are the black vertices. And so now you know what this matrix K tilde is. It only depends on the connection and the multiplicities, and that's the left-hand side. You could take its determinant. It's a square matrix, so it has a determinant. Okay, so now I have to tell you about the right-hand side. We know what the webs are, the multiwebs, but I have to explain what the trace of a multiweb is, because the trace is going to depend on the entries of the matrices, on the connection. And this is the hardest slide to digest of this talk, even though it fits on one slide and there's nothing really sophisticated going on, but somehow it took us a long time to understand. But let's see, what can I say? This is essentially a representation theory kind of object. It's a Reshetikhin-Turaev invariant, if you like, but I don't want to use any kind of fancy-ish language. So let me run through it here quickly. Let's first assume that our multiweb has multiplicities only 1 or 0 at the beginning. Then I'll tell you how to do it for higher multiplicities. So we can just throw out all the edges of multiplicity 0. They don't really play any role. And so unlike this example, let's assume that all the edges have multiplicity 1, and we ignore the edges of multiplicity 0. So now I have a vertex here with multiplicity n. So it's got n edges around it. And I have a vector space there of dimension n. And I'm going to take that vector space, a little copy of that vector space on each half edge around that vertex. So v1 through vn are all copies of Rn. And they all have the same basis, which I'm calling E1 through En, standard basis. So now I've got n vector spaces, each of dimension n. And I'm going to take their tensor product. So this is a big vector space of dimension n to the n, right? It's kind of annoying, but it's big. But can't avoid it. And inside that tensor product, the tensor product of of these n vector spaces, there's a special vector called the codeterminant, special tensor. Well, it's a tensor because it's an element of a tensor product. This thing is called the codeterminant, and here's the formula. It looks kind of like a determinant, but the entries here are not multiplied together. It's just a tensor product of, so E1 sigma 1 is the sigma 1th basis element of the first vector space, and so on. And you sum them up with the sign. What's special about this codeterminant? Well, it happens to be invariant under SLN base change. If I change basis here, if I don't take the standard basis but some other basis, this as long as I take that same base change in all the vector spaces at the same time, the codeterminant doesn't change. That's a little exercise which I'll leave for you. Okay, so that's what happens at a black vertex. At the white vertex, you do the same, except you use the sort of dual vector space. You pretend like you're in the dual vector space for Rn. But the formula is the same. And then, how do we define the trace of our web? Well, right, this notation contains a lot of information, but we have this tensor product of all these tensor products over all the black vertices. Along each edge, I've got a linear map from V1 to the corresponding vector space over here. That's called phi BW. Then I can contract along every edge, every component of this tensor with the corresponding part of the white vertex, and I get a number in the end. Okay, I told you it was hard to digest, but it's a little bit mysterious, and even doing it on a computer is kind of hard because there's a sort of exponential amount of computation to do that. Right? Even though it's linear algebra, it's big linear algebra. Let's ignore, well, okay, so you do need to worry about the order, not just the cyclic order. So we put that little mark, that little tilde there, that indicates where the cyclic order starts. And the order at a black vertex and the order at a white vertex are, one goes counterclockwise, the other goes clockwise. Let's ignore that part for now. If we have edges of higher multiplicity, you just do something very simple. If you have an edge of multiplicity bigger than 1, you replace it with that many copies of the edge in parallel, and then you compute the trace of this graph, of this web, and then you divide by the corresponding factorial. Again, that's not something you have to worry about either. Let's just do a quick example of evaluating the trace on a very simple graph. This is part of my square ice model. Suppose that one of my molecules looks like this L shape. What's the trace? Well, now, remember, at the central vertex, I have a vector space of dimension 2. At the black vertices, I have a vector space of dimension 1. And so along every edge, I've got a 1×2 matrix. That's my connection, C1, D1, and so on. And the codeterminant at this white vertex looks like that. It's just E1, E2 minus E2, E1. And the codeterminants, right, these guys are just one-dimensional vector spaces, so their codeterminants are just 1 or something, E1, I guess. And then you map it over, and these two entries get plugged in to this tensor, and you get C1, the first entry of the first guy, times D2 minus D1 C2, and sure enough, the trace of this thing is the determinant of that 2×2 matrix, where the columns are coming from the connection along those two edges. Okay, so if you trace through what I said on the previous slide, this is what pops out of the determinant. And if we want to do probability, it's good that all the traces are positive numbers, and because we want to count things positively, we don't want things to have negative weight if we're trying to do probability. So in order to configurations have positive weight, we need these determinants of all different kinds of molecules to be positive, which means that this matrix, if you read around the white vertex starting from the cilium, you make a 2x4 matrix. That if that matrix is in the positive Grassmannian, that is all maximal minors are positive, then all the traces will be positive and you can do probability.
So I guess that also explains the equation you have before the Plucker relation.
Yeah, that's right. The equation for that we had before from this one, that's the Plucker relation for the minors of a 2x2 matrix, 2x4 matrix. Okay. So here's our theorem, and here's the proof, right? We now know what the left-hand side is. It's a determinant of this matrix constructed from the connection. We know what the right-hand side, the trace is this linear algebraic thing. We're summing over connections, and the proof is expand on both sides, rearrange. Okay. It still takes, 5 or so pages in our papers, right? The hardest part is getting the signs right, but that's the way representation theory is. The signs are the hardest part of any combinatorial calculation. Okay, applications. How are we doing on time? Now, the application they started with was superimposing 2 dimer covers and seeing where the loops went. So let's do that. When I superimpose 2 dimer covers, I get a two multiweb. Every vertex has, a 2-dimensional vector space, and there's 2 edges coming out of it, which may be the same edge. Kind of like here. So if I want a 2 multiweb, I should ignore the colors here. Just pretend like both colors are black. I shouldn't necessarily think of a 2 multiweb as coming from a union of single dimer covers, but anyway, I was too lazy to remake the picture in black. Okay, so if we have a 2 multiweb, the trace has a nice formula, there's a nice simpler way to think about the trace. Right? What is a 2 multiweb? It's a union of loops and doubled edges. What is the trace of such a multiweb? Remember, our graph is now, and I should say, let's suppose that we have an actual connection, an SL2 connection, so all the matrices are determinant 1. And they're 2x2 matrices. The lemma is that the trace of a multiweb of this type is the product over the loops that you see here. And for each loop, you can take the actual, I should have used a different notation here, the matrix trace of the monodromy of the connection around the loop. So, as I move around the loop, I can compose the connection. I can compose the sort of the parallel transports along each edge. And when I get back, I have an actual matrix in SL2. I can take its trace. That's the trace of the monodromy of the connection. And for SL2, it doesn't matter which way you go around because the trace of the matrix and the trace of the inverse are the same. So the loops don't have to be oriented. So that's the theorem, and it's not very hard to prove. It's kind of similar to the proof we gave, the example. If you have a doubled edge, the trace contribution from a doubled edge is just 1. It's like the determinant of an SL2 matrix, and it gives you 1. So you only count the non-trivial loops here in this formula. But in particular, if our connection is just the identity, right? We just have the trivial connection. Then the trace of a configuration is just 2 to the number of loops because each big loop has the trace of the identity, and that's 2 for SL2. Well, this is good because when you superimpose 2 dimer covers, each loop can come from the 2 dimer covers in 2 different ways, exactly 2 different ways. It can be blue, green, or it can be green, blue. So each loop really does get a contribution of 2. And this was the model that we started out thinking about, right? We superimposed 2 dimer covers, That's the one we want to understand sort of probabilistically. We want to ask probability questions about the union of two dimer covers. And so this is the natural weight that we should assign to a configuration. Okay, so that's right. So how does the theorem help? Well, now we're going to ask a more sophisticated question. Suppose that I puncture some faces in my graph, like these three faces. I can ask, what's the probability that when I superimpose these two dimer covers, I get a loop which surrounds some of those punctures and not others? Right? What's the probability for this natural measure, the measure coming from the union of two dimers, that our loops have a given, our collection of loops has a given sort of isotopy class in the complement of those punctures? Right? What's the probability that, you know, these two get surrounded, but I mean, anyway. Does that make sense? What's the probability that in a union of two dimer covers, I have a given, the set of closed loops has a given isotopy classes? If I ignore the topologically trivial loops, the contractible loops, and only take into account the ones which surround the punctures, one or more punctures. This is something we now have, the technology allows you to count that. This is what I want to explain. This is the main idea of the whole construction. So how do we do it? We take a flat SL2 connection on my graph. I have a graph just like this one, which is a planar graph with some punctured faces. I'm going to take a flat SL2 connection. What does it mean to be flat? It just means that the monodromy around a face which is contractible is trivial. Then the formula for the trace of a multiweb now is slightly different. It's not just 2 to the number of loops anymore, but it's 2 to the number of loops times for every loop which surrounds one or more punctures, I have to take into account the trace of the monodromy of that loop. So the idea is that by varying the connection here, the flat connection, this trace can detect the homotopy type of the loops in my union. Right? If I just take let me not belabor that point, but this is the main idea, is that by changing the connection, I can detect where my loops are going. And so if I look at my determinant with my connection, our theorem says it's a sum of traces of loops. But when you have a flat connection, you only care about the isotopy classes of the simple closed curve system in the complement of those punctures. And so then this sum can be grouped into isotopy classes, and there's some coefficients, and the coefficient is the one we care about. That's the probability that at least when I normalize, it's the probability that my union of two dimer covers has a particular isotopy class. And now we're kind of saved by this theorem of Fock and Goncharov, which is really representation theory, that these traces of isotopy classes of simple closed curve systems form a basis for regular functions on the character variety, which is to say, as we vary the connection among all flat connections, we can, these functions are linearly independent, and therefore we can extract the coefficients in principle. Corollary is that the coefficients, that is the probabilities, are determined by this function of the flat connection. Unfortunately, in general, we don't really know how to extract the coefficients from this. I mean, we can compute the left-hand side, and now it's some sort of infinite linear algebra problem to extract the coefficients. I don't know a quick way to do that. However, we can do it on some simple graphs, like this is the case of a torus. An annulus. If I have a double dimer cover of an annular region in the plane, you can ask, for example, how many loops wind around the annulus? That's some random number. What's the distribution of that random number? And it has kind of a very pretty answer, again. If you take them in the limit as the mesh size goes to 0, the mesh of the graph, this distribution only depends on the conformal modulus of the annulus. And if I call tau the conformal modulus, and q is e to the minus pi tau, as usual, then the generating function for the probability of having exactly j loops, you make this into a generating function, has a very pretty formula, which some number theorists in the audience might recognize. I don't know, involving some theta functions. This is another case where, in this case, there's no boundary. Before we had some boundary and we were computing connections. This is the analog without boundary, but still we get very, very beautiful formulas for these generating functions. Okay. To finish up, let me, in the last 5 minutes, let me talk about SL3. The previous thing was superimposing 2 dimer covers, and I used SL2. Now I'm going to superimpose 3 dimer covers, and my underlying structure group is going to be SL3, my gauge group. And here I just use my computer to superimpose 3 dimer covers, and you don't see any large structure, but secretly there's some structure in there. There's sort of a backbone or a spine. The idea is that when you color, if you keep track of which dimer cover, if it's just a triple of dimer covers, you keep track of which one is red, green, and blue, then you can extract, with the appropriate tool, a reduced something called a reduced web inside that. And that reduced web is some kind of spine inside there. And it has, even though the spine itself is not really canonical, its topological type, that is how it connects the boundary vertices together, is canonical. So only the sort of isotopic class of this blue curve is well defined. Now let me explain. I'll explain that picture. First there's one more definition. When you're dealing with SL3, there's these things called 3 webs, which are almost the same as 3 multiwebs, right? What's a multiweb? A multiweb is something that sits inside an ambient graph. A 3-web itself is just an abstract trivalent graph, bipartite trivalent graph. And if I have a multiweb here, right, so that means the edges have multiplicity 0, 1, 2, or 3. And at each vertex, the sum of the degrees, each vertex has multiplicity 3. So what happens is that I get some trivalent, some triple edges, and then I have some double edges, but each double edge is part of a chain of edges of which alternates 2, 1, 2, 1, 2, 1, and may end at a trivalent vertex, like this. So that's the typical parts in a multiweb. And associated to that is a real web, a 3-web, where you just throw out the trivalent edges, the multiplicity 3 edges, and the chains of 1s and 2s, they just become paths here. So the vertices over here, the trivalent vertices remain, but then they're connected by these, on the left, by these 1, 2, 1, 2 chains. So this is the multiweb, that's a web. They're almost the same object. The multiweb has a trace, the web has the same trace. At least for a flat connection, the trace of the web and the trace of the multiweb are the same. These 3 webs are something that representation theorists care about for the representation theory of SL3. And in particular, there's a notion of reduced web. Well, let's see. I don't really have time to tell you what the representation theory, how it's related to the representation theory, but let me just briefly say that there are certain relations, web reductions or scheme relations for 3 webs, one of which is if you have a loop which is topologically trivial, then you can replace it with, you just replace it with a 3, throw it away, and multiply everything else by 3. If you have a bygone, you can remove it from your graph, and you get a factor of 2. And if you have a square face, you can write this web, which is connected which is part of a larger web, you can replace it with a linear combination of 2 different webs, which are both simpler. So there's a way to take a web with possibly complicated web and replace it with a linear combination of simpler webs. And when there are no faces of degree 0, 2, or 4, then we say the web is reduced. So every web can be rewritten as a linear combination of reduced webs. And the nice thing is that the reduced webs can be sort of classified in a very simple way, especially if you're on a surface. This is what I just said on the previous slide. For every 3 multiweb, those gain relations preserve the trace. The trace of, if you have a 3 multiweb, its trace on a graph on a surface with a flat connection, I'm sorry, I'm going too fast. For a 3 multiweb on a graph on a surface with a flat connection, its trace can be written as a linear combination of traces of reduced webs, isotopy classes of reduced webs. So our determinant, which starts out as a sum of traces, can be written as a sum of traces of reduced webs. And the analog of the Fock-Goncharov theorem for SL2 is a theorem of Sikora and Westbury that says that traces of reduced webs do also form a basis for the regular functions on the SL3 character variety of the underlying surface. And therefore, our determinant, which we can compute, can be written as a sum of some coefficients, but the sum is over all the isotopy classes of reduced webs on the surface, and by the result of Sikora and Westbury, the CK now can be extracted, in principle, by some linear algebra from the determinant. So we're in good shape because this is something we can compute, or at least our computer can compute, and with some linear algebra, we should be able to extract the coefficients. But again, that's kind of a hard, infinite dimensional linear algebra problem. We don't really know how to do that effectively. But the answer is that, the upshot is that we can determine the sort of topological type of a superposition of 3 dimer covers. And again, here's the answer for an annulus. That's the case where calculations are feasible, easy enough to do. On an annulus, every reduced web, this is a slightly non-trivial lemma. Every reduced web is a union of loops which are oriented, which in this case they're they're not really oriented, but there's 2 different kinds of loops because there's a black and white coloring, and each loop you can think of each loop as a 1-2-1-2 chain. And depending on whether the 2's occur at the beginning of a white or black, it has one orientation or the other. And if your annulus has so you can take, you take 3 dimer covers of the annulus, you superimpose them, you reduce the corresponding cloud to a reduced web. So it's got a certain number of edges loops going clockwise, certain number going counterclockwise. If there's, I going clockwise and j going counterclockwise, there's some probability of that event. And when you sum up the generating function over all I and j in the scaling limit, it again gives you some some interesting formula, depending only on the conformal modulus of the annulus. It's again a conformally invariant quantity associated to an annulus. And going back to the original problem with boundary, this was again a result with no boundary. If you do have some boundary points, you can talk about reduced webs with boundary. So they're webs where all the internal vertices are trivalent and the boundary vertices are degree 1. And these kind of webs, the probability of such a web can also be computed, and it's again conformally invariant, depends on the image of the points in the upper half plane, and there are again some pretty rational expressions of the boundary points here. So here's, in that, sorry, if you go back to this picture, if you take this picture and you look for the, reduced web inside it, I sort of, this picture is not well defined, but up to isotopy it is well defined. It is a hexagon with 6 legs like this. And so the probability that you get this topological type of reduced web is given by this expression where Z1 through Z6 are the image of the points in the upper half plane. Thank you.
We do have time for questions. Do please wait until you get a microphone, because there might be people in the overflow room as you think about questions. I will also have a message from our sponsor, which is that as you later today go to special sessions, be careful to check where your session is, especially sessions that don't take up all 5 days of the schedule might have some room changes. Of course, if you go to the usual room, you might unexpectedly learn some wonderful mathematics you didn't expect to hear about. So with that, let us see whether there are questions. And again, I see one there. Microphone is not yet there.
Hello? Yeah. So is there a reason to expect the limiting probabilities to be conformal invariants of the shape? Like why is that happening?
Yeah, very, very good question. That's a kind of a hard theorem. If you talk to a physicist in the audience, some of them may give you some argument, but I don't have a good argument except that it's a theorem, and it's not known that all probabilities that you care about are conformally invariant for the double dimer model or triple dimer model, but these ones are. And it only comes out of the calculation. We don't really know a priori that they are conformally invariant.
So Rick, you showed the annulus, so I assume you can do homogeneous surfaces as well, and can you give loops around the non-contractible
That's right.
cycles a different weight than 2? Or?
It's a little more complicated, and we haven't quite worked out all the sign issues, right? I said signs were the biggest headache. If you have a planar domain, somehow the signs are much easier to deal with, but in principle, you can do it on a arbitrarily closed or higher genus Riemann surface, even with boundary. Same results should hold, but it has not appeared, it's not been written down.
And the non-contractible loops around, can you give them a different weight than 2, or they also have to be 2?
The non-contractible loops, yeah, they can.
They can have.
You can change the trace by changing. If you change the flat connection, right, you can give them any weight you want.
And when you talk about high genus surfaces, do you glue them out of squares?
Not necessarily. No. Any conformal structure, the resulting thing only depends on the conformal structure of the surface. That's the theorem. So you don't have to. All you need
is a bipartite graph, right?
Yeah, you need the bipartite graph to sort of approximate in a conformal way the surface, and that's a slightly non-trivial business. But if you have a quadratic differential on the surface, then you can approximate the square grid with respect to the underlying Euclidean structure, and then that will work.
In your square ice model, the codeterminant that you obtained was a skew object or a skew tensor. Is that generic, or was that an accident?
No, it's always, the codeterminant is always that maximally, it's the anti-symmetrizer. Sorry, where's that? Yeah, it's that one.
So if you go to the next slide.
Yeah.
Sorry, yeah, this one here. So this particular example, it's skew, and you're saying that's always the case.
It's always the case, yes.
Yes, thank you.
It looks like we're mostly okay, and I did learn, if nothing else, that representation theory can give you a science headache. In order to help Rick with his work-life balance down the road, the Kiwis have kindly provided a present to remember his visit by, and let's thank Rick again and buy him a cup of coffee.
Thank you.